Welcome to this coding problem walkthrough. In this session, we'll explore problem number 2182 titled Construct String with Repeat Limit. We'll analyze the problem, discuss possible approaches, and break it down step by step. Let's dive in. In this problem, you are given a string S made up of lowercase English letters, along with an integer repeat limit. The task is to construct a new string by rearranging the characters of S while adhering to two specific constraints. First, the new string must be the lexicographically largest possible string that can be formed using the characters of S. Second, no single character can appear consecutively more than repeat limit times in the new string. The goal is to return this resulting string. For the input, S is guaranteed to be a non-empty string with a length between 1 and 100,000, and the repeat limit is a positive integer between 1 and 10,000. The output will be the constructed string that satisfies both constraints. To better understand this problem, let's look at an example. Suppose the input string is S equals chazask and the repeat limit is 3. The output in this case would be skakak. Here, skakak is the lexicographically largest string that can be formed while ensuring that no character appears more than 3 times consecutively. For instance, the character Z appears twice in a row, and the character C appears 3 times in a row, which is valid under the given limit. This output string satisfies all the constraints and represents the optimal solution. Now, consider another example. For the input S equals ababab with repeat limit equals 2, the output is baba. In this case, the lexicographically largest string is achieved by prioritizing the largest letters first while ensuring that no character exceeds the consecutive repeat limit of 2. For example, the character B appears twice in a row before switching to A, and then alternates to maintain the constraints. This solution ensures that the string is valid and adheres to both the lexicographical and repetition rules. It's important to think about some key edge cases for this problem. First, if the input string contains only one type of character, the output string will be formed by repeating that character in groups of up to repeat limit. For instance, if S equals AAAA and repeat limit equals 2, the output would be AA because no more than 2 consecutive repetitions are allowed. Next, if the string is small but the repeat limit is very large, the output will simply be the lexicographically largest permutation of the string. For example, if S equals ABC and repeat limit equals 100, the result will be CBA. Finally, when dealing with a large string and a small repeat limit, the solution must carefully alternate between characters to ensure the constraints are met while still prioritizing lexicographical order. These scenarios highlight the importance of balancing the constraints with the goal of maximizing the string's order. To solve this problem, one straightforward yet naive approach is the brute force method. Here, we generate all possible permutations of the string and filter out the ones that violate the repeat limit. Once we have the valid strings, we can simply select the lexicographically largest one as the result. While this approach guarantees correctness because generating and sorting all permutations ensures we eventually find the best solution, it is highly inefficient. The process of generating all permutations has a factorial time complexity, O(n), which quickly becomes impractical as the length of the string increases, especially if the string contains repeated characters. Additionally, checking each permutation against the repeat limit adds yet another layer of computational overhead. This makes the brute force approach infeasible for larger inputs and unsuitable for real-world use cases where performance matters. A more efficient and scalable solution is the greedy approach, which leverages a priority queue, or max heap, to construct the result string dynamically. The process begins by counting the frequency of each character in the input string. These frequencies are then stored in a max heap, allowing us to efficiently access the largest lexicographical character at any point. The main idea is to repeatedly append the largest valid character to the result string while adhering to the repeat limit. If appending the largest character would violate the repeat limit, we temporarily skip it and use the next largest character from the heap. After appending this alternate character, the skipped character is reinserted into the heap if it still has remaining frequency. By dynamically managing which characters are appended and when, this approach avoids generating unnecessary permutations and directly constructs the result string. The heap ensures that we always have efficient access to the next best character, and the repeat limit condition is handled dynamically throughout the process. The greedy approach with a priority queue is chosen due to its efficiency and adherence to the problem constraints. Its time complexity is O, n log k, where n is the length of the string and k is the number of unique characters. This is because inserting and removing elements from the heap involves logarithmic operations, and each character is processed only once. The space complexity is O, k, as the heap stores only the unique characters. This strategy balances efficiency with correctness. A key insight is that the repeat limit can be handled dynamically by temporarily skipping characters and reinserting them into the heap, which avoids violating constraints while ensuring the result string remains lexicographically optimal. Compared to the brute force method, which is computationally infeasible for larger inputs, the greedy approach directly constructs the result string and scales well with input size. While other greedy methods, such as sorting without a heap, may seem simpler, they lack the flexibility needed for making frequent dynamic decisions. Therefore, the chosen strategy is both practical and scalable, making it the best fit for this problem. In this problem, we need to build the lexicographically largest string from a given string S, while ensuring that no character appears more than repeat limit times consecutively. To achieve this, we start with two key steps. First, we count the frequency of each character in the string. This can be done using a dictionary or a list, where the keys represent characters and the values represent their counts. For example, if the string is app, the frequency count would give us 2, B, 2, C, 1. This frequency count is crucial because it gives us the distribution of characters, which we will use to construct the result. Next, we initialize a max heap to manage the characters in descending lexicographical order. By pushing tuples of the form ord C, C into the heap, we ensure that the largest characters are prioritized first. This is because the heap will sort by the negative ASCII values, effectively reversing the order. The max heap allows efficient retrieval of the largest available character, which is central to our goal of constructing the largest possible string. Now that we have the frequency counts and the max heap ready, we can move on to constructing the string while adhering to the repeat limit. We start with an empty result string res. While the heap is not empty, we pop the character with the highest lexicographical value, which we'll call C1, along with its frequency. We then determine how many times C1 can be appended to the result without exceeding the repeat limit. If the limit is not violated, we append C1 up to repeat limit times. However, if appending C1 would exceed the limit, we append it fewer times, just enough to avoid consecutive repeats. If C1 still has a remaining frequency after this step, we push it back into the heap for future iterations. If the heap is not empty, we then pick the next largest character, C2, append it once to res, and continue processing C1. This alternation ensures that we respect the repeat limit while utilizing the largest characters available. Additionally, we handle specific edge cases, such as when the repeat limit is very small, by alternating more frequently between characters. If the string contains only one distinct character, we ensure we honor the limit and truncate the result if necessary. Lastly, if the heap becomes empty with unresolved frequencies remaining, we terminate the process early, as no further valid construction is possible. Several key insights make this algorithm efficient and effective. First, the max heap is essential because it always gives us the largest available character, which is crucial for constructing the lexicographically largest string. Without this, we would not be able to prioritize characters efficiently. Second, by carefully managing the repeat limit, we ensure that the resulting string is valid while maximizing the inclusion of high-priority characters. This balance is achieved by alternating characters whenever necessary to avoid consecutive repeats. Finally, reinserting characters with residual frequencies into the heap ensures that no characters are prematurely discarded and all frequencies are utilized. To implement this algorithm, we use three main data structures: a frequency dictionary to track the count of each character, a max heap for efficient retrieval of the largest character, and the result string, which is constructed iteratively by appending characters. Together, these components work seamlessly to produce the desired output. Let's analyze the time complexity of this algorithm. The most expensive operations involve the heap. Inserting and removing elements from the heap each take O log n, where n is the number of distinct characters in the input string. The main construction loop processes each character based on its frequency, resulting in a total of O, m log n, operations, where m is the total number of characters in the string S. Thus, the overall time complexity of the algorithm is O, m log n. To illustrate, consider the input s equals a app with repeat limit equals 2. First, we calculate the frequency count, a 3, b, 2, c, 1. Next, we initialize the max heap, which stores characters as -97, -98, b, -99, c. During string construction, we start by appending a twice, as the repeat limit allows. The remaining frequency of a is 1. Next, we append b once, reducing its frequency to 1. We then reinsert a into the heap and continue this process until all characters are used. The final output is a back, which adheres to the repeat limit while being lexicographically largest. This example demonstrates how the algorithm efficiently balances constraints while achieving the desired result. To solve the problem, we start by importing the counter class from the collections module, which will help us count the frequency of each character in the input string. Inside the solution class, we define the method repeatLimitedString that takes the input string s and the repeat limit. First, we calculate the frequency of each character using counter and then sort these characters in descending order based on their ASCII values, so we can process the largest characters first. The sorted characters are stored in sorted_chars. We also initialize an empty list called result, which will store the characters of our constructed string. Now we enter a while loop that will continue as long as there are characters left in sorted_chars. In each iteration, we take the largest available character, which is the first item in the sorted list, and determine how many times it can be added to the result without exceeding the repeat limit. This count is the smaller value between the character's remaining frequency and the repeat limit. We then append this character to the result list up to the allowed count and reduce its frequency accordingly. If there are still occurrences of the current character left, we need to handle the repeat limit by inserting a smaller character next to ensure the rules are followed. To find the next largest character, we iterate through the remaining characters in sorted_chars, starting from the second largest. If a character with a positive frequency is found, we append it to the result list, decrease its frequency by 1, and set a flag next _char_found to true. If the next character becomes exhausted, meaning its frequency drops to 0, we remove it from sorted_chars. This ensures that we maintain an updated list of available characters. If no valid next character is found during this search, we break out of the loop entirely, as it would mean we can no longer add to the result while respecting the repeat limit. On the other hand, if the current character is completely exhausted, it is removed from sorted_chars to avoid unnecessary processing. Finally, once the loop completes, we return the constructed string by joining all the characters stored in the result list. This approach ensures that the string adheres to the repeat limit while maintaining lexicographical order as much as possible. In this implementation, we start by importing the necessary libraries and defining our solution class with the repeatLimitedString method. The first step involves counting the frequency of each character in the input string using an array of size 26, where each index corresponds to a letter in the alphabet. We iterate through the string, incrementing the frequency count for each character. Next, we create a max heap to store the characters in descending order based on their ASCII values. This allows us to prioritize the largest characters first when constructing the result. We then iterate through the frequency array, adding characters with non-zero frequency to the heap. Finally, we initialize a string builder to construct the resulting string. At this point, we're prepared to start processing the heap to build the desired output string while respecting the repeat limit. Now, we enter the main loop where we process characters from the max heap. First, we take the largest available character by polling the heap. We calculate how many times this character can be appended to the result, which is determined by the minimum of its frequency and the repeat limit. Using a simple loop, we append this character to the result up to the calculated count and then reduce its frequency accordingly. If the character still has remaining occurrences, we need to ensure that the repeat limit isn't violated by inserting an alternate character before reusing it. To do this, we check if the heap has another character available. If it does, we poll the next largest character, append it to the result, and reduce its frequency. If the alternate character still has occurrences left, we reinsert it into the heap for future consideration. Similarly, the original character is reinserted into the heap to be processed later. If no alternate character is available, we break out of the loop as it's impossible to continue without violating the repeat limit. Finally, the method concludes by returning the constructed string as the result. The combination of the max heap and careful frequency management ensures that the output string adheres to the repeat limit while maximizing lexicographical order. This approach efficiently balances the problem constraints and provides the correct solution. To solve this problem, we start by analyzing the input string and repeat limit. In example 1, the input string is chazask and the repeat limit is 2. First, we count the frequency of each character, resulting in C4, Z1, 1. Next, we sort the characters in descending order based on their ASCII values, which gives us Z. The goal is to construct the output string by repeatedly taking the largest available character while respecting the repeat limit. We start with the largest character, Z, and add it to the result up to the repeat limit, which is 1 time in this case. This gives us the intermediate result, Z. The frequency of Z is then decreased to 0, and it is removed from the sorted list. Moving on, the next largest character is C. We add C up to the repeat limit, which is 2 times, resulting in Z, C, C. The frequency of C is decreased to 2, and we continue building the result string from the remaining characters. Now, we need to ensure that we avoid repeating the same character more than the repeat limit consecutively. Since C is the last character added, we look for the next largest available character, which is A. We add it to the result, resulting in Z, C, C, and decrease its frequency to 0. This removes A from the sorted list, leaving only C. With C still available, we add it up to the repeat limit again, which is 2 times, giving us the final result, Z, C, 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 C. The frequency of C is now reduced to 0, and the sorted list is empty. The resulting string is SCAC, which satisfies the constraints of the problem as no character exceeds the repeat limit consecutively and the characters are chosen in descending order of priority. In example 2, the input string is ababab with a repeat limit of 3. First, we count the frequencies, resulting in A, 4, B, 3, and sort the characters in descending order, giving B, A. We start with the largest character, B, and add it to the result up to the repeat limit, which is 3 times. This gives us the intermediate result, B, B, B. The frequency of B is decreased to 0, and B is removed from the sorted list. The next available character is A, so we add A up to the repeat limit, resulting in B, 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 A. The frequency of A is decreased to 1, and we proceed to handle the remaining characters. With only 1 A left, we add it to the result, resulting in B, 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 A. The frequency of A is now reduced to 0, and the sorted list becomes empty. The final output string is Baea, which respects the repeat limit while prioritizing the largest characters first. Now, we consider a simpler case in example 3, where the input string is ZZZZ and the repeat limit is 1. This example demonstrates how the algorithm handles a case where the repeat limit is very restrictive. In this case, we start by counting the frequencies, which gives Z, 4, and sorting the characters in descending order results in Z. Since the repeat limit is 1, we can only add Z 1 time before needing an alternate character. We add Z to the result, decreasing its frequency to 3. At this point, we attempt to add a different character, but none are available. As a result, we stop building the string, and the final output is Z. This example highlights how the algorithm gracefully handles scenarios where no alternate characters are available, ensuring the constraints are always respected while prioritizing the largest characters. The time complexity of this solution can be analyzed step by step. First, we count the frequencies of each character in the input string using the counter function. This process requires O(n) time, where n is the string's length, since the function iterates through the entire string. Next, we sort the unique characters in descending lexicographical order using the sorted function. If there are k unique characters, this sorting step takes k*log k time due to the nature of sorting algorithms. Now, as we move into the main algorithm, the while loop iterates over the sorted list of characters. In the worst case, each character is processed individually until its frequency is exhausted. Operations within the loop include appending characters up to the repeat limit, which takes repeat limit, time, and searching for the next largest character, which involves iterating over the remaining characters in the sorted list and can take time in the worst case. Removing a character from the list when its frequency becomes 0 is an O1 operation. Together, these steps form the foundation of our time complexity analysis. Now, when we consider the worst-case scenario, the nested for loop could be executed for each character in the sorted list. This results in a complexity of k squared for this part of the algorithm. Combining all steps, the overall time complexity can be expressed as n plus k asterisk log k plus k squared. However, since k is bounded by 26, the number of lowercase English letters, both k asterisk log k and k squared, are effectively constant time operations. This allows the overall time complexity to simplify to n, as the linear pass through the string dominates the computation. Moving on to space complexity, the counter dictionary that stores the frequency of each character requires k space, where k represents the number of unique characters, which is at most 26. Similarly, the sorted _chars list, which holds the unique characters in descending order, also requires k space. Additionally, the result list, which stores the final constructed string, requires n space in the worst case, as it may need to store all n characters of the input string. Combining these, the total space complexity is k plus n, which simplifies to n, as k is constant and dominated by the n space required for the result. Comparing this optimized approach to a brute force solution highlights the efficiency of the given algorithm. A naive approach might involve repeatedly appending characters to the result string while checking and enforcing the repeat limit. This would result in frequent string concatenations and redundant checks, leading to a higher time complexity, potentially n squared. In contrast, the optimized solution leverages character frequencies and presorting to efficiently enforce the repeat limit and build the result string. This reduces the time complexity to n, making it significantly faster and more scalable for larger inputs. Now, let's break down the time complexity into best, average, and worst-case scenarios. In the best case, where the input string consists of only one unique character, the algorithm simply appends up to the repeat limit and terminates. This results in a time complexity of n. In the average case, for a typical input with multiple unique characters, the algorithm processes each character sequentially after sorting, maintaining a time complexity of n. Even in the worst case, where all k unique characters are processed individually, the constant bound on k ensures that the time complexity does not exceed n. Mathematically, the dominant factor in the time complexity is the linear pass through the string n, combined with the sorting step k asterisk log k. Since k is constant, the overall complexity remains n. Similarly, the space complexity is dominated by the size of the result list, which is n, ensuring the algorithm remains efficient in both time and space. When solving this problem, there are several common mistakes that can trip you up. One of the most frequent issues is ignoring edge cases. For example, failing to consider situations like an empty string, strings with repeating characters, or when the repeat limit is set to 0 or 1. These scenarios might seem rare, but they often reveal hidden bugs in your implementation and can cause runtime errors or incorrect outputs. Another mistake is overcomplicating the solution. Some might attempt a brute force approach, like generating all permutations of the string, instead of using a greedy method. While this might work for small inputs, the factorial time complexity of permutations makes it completely infeasible for larger strings. A third common pitfall is mismanaging the repeat limit, which can happen if you don't enforce the limit properly while constructing the output string. This could result in outputs that violate the problem's constraints. Lastly, inefficient sorting logic can cause problems too. If you repeatedly sort the string inside a loop, it significantly increases the time complexity, sometimes to n superscript 2 log n, or worse. Instead, sorting the string once up front is generally more efficient. Another common issue arises from incorrect usage of priority queues or max heaps. For instance, if you fail to reinsert characters back into the heap after enforcing the repeat limit, you might end up with missing characters or an output that doesn't match the constraints. To avoid this, you need to carefully manage the heap to ensure all characters are processed correctly. Now, in terms of interview preparation, one key insight is that problems involving constraints on character frequencies often benefit from greedy algorithms combined with a data structure like a priority queue or frequency map. A recurring pattern to watch for is when constraints involve limiting consecutive repetitions. In these cases, you'll want to maintain a count of characters and use a structure like a max heap to enforce the limits efficiently. Additionally, it's important to explain your trade-offs. For example, you should be able to articulate why a greedy approach is optimal for this problem, as opposed to brute force, which becomes impractical due to its high time complexity. Finally, prioritize practicing the implementation of data structures like priority queues and custom sorting logic. These skills are essential for solving not just this problem, but many other string manipulation challenges. This problem also shares similarities with several related problems that you might encounter during practice or interviews. For instance, in problem 767, Reorganize String, you're tasked with rearranging characters in a string so that no two adjacent characters are the same. Similarly, problem 621, Task Scheduler, involves scheduling tasks with cooldown periods while adhering to specific constraints on the execution order. Another related challenge is problem 358, Rearrange String k distance apart, which extends the concept by enforcing a general distance constraint between characters instead of a repeat limit. Finally, there's problem 451, Sort characters by frequency, where the goal is to sort characters based on their frequency in descending order. For alternative approaches to solving the current problem, one option is brute force using permutations. While this method involves generating all possible permutations of the string and filtering out those that meet the repeat limit, it's highly inefficient due to its factorial time complexity. A more practical approach is the greedy method combined with sorting. In this strategy, you sort the string by frequency and then construct the output while adhering to the repeat limit. Although this is more efficient than brute force, it can still be suboptimal if you repeatedly sort inside loops, so it's important to optimize where possible. An even more effective approach is using a greedy algorithm with a max heap. Here's how it works: you use the max heap to repeatedly extract the character with the highest frequency while ensuring that the repeat limit is enforced. If the most frequent character reaches its limit, you can insert a less frequent character in between, then reinsert the original character back into the heap for further processing. This method is both time efficient, with a complexity of n log k, and handles the problem's constraints cleanly. However, it does require familiarity with heap operations, so make sure you're comfortable with implementing and managing heaps before attempting this approach. Overall, this strategy is optimal not just for the current problem, but for a variety of scenarios where you need to balance frequency constraints with efficiency. Great job! To sum up, we tackled problem number 2182 by exploring various approaches and selecting the most effective one. Remember to focus on constraints and optimize your solutions. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!